Let me ask you something. Have you ever needed to log into a server on the other side of the world, fix a broken configuration, and then log out, all while sitting in your pajamas at 2 a.m.? That magic is called SSH. It stands for Secure Shell, and it is the backbone of remote server administration. But here is the spooky part: how does SSH actually keep your connection safe? How does it know that the computer on the other end is really your server, and not some hacker waiting to steal your password? Today, we are going to pull back the curtain on SSH. We are going to look at the handshake, the encryption, the keys, and even some common mistakes that can make your secure shell about as secure as a cardboard door. By the end of this video, you will understand not just how to use SSH, but how it works at the protocol level. Let us dive in. First, let us set the stage. SSH was created in 1995 by a Finnish researcher named Tatu Ilonen. Before SSH, people used protocols like Telnet or Login. Those old protocols sent everything in plain text. Your username, your password, every command you typed, it was all visible to anyone on the network. Imagine shouting your bank PIN across a crowded room. That was Telnet. SSH was designed to fix that. It encrypts everything between your local machine and the remote server. But encryption is not simple. You cannot just wrap data in a magic cloak. You need a way to agree on a secret key, prove your identities, and then scramble the data so only the other side can unscramble it. That process happens in three main phases: the TCP handshake, the key exchange, and the authentication. Let us walk through each one. The first thing that happens is the boring but essential TCP handshake. Your SSH client, say a terminal on your laptop, sends a SYN packet to the server on port 22. The server replies with SYN ACK. Your client sends an ACK back. Done. This is just the connection being established. But do not blink, because right after that, the real cryptography begins. The server immediately sends its host key. This is a long, unique cryptographic key that identifies the server. You have probably seen that scary message the first time you connect to a new server: the authenticity of host can't be established. It asks you to confirm the fingerprint. That fingerprint is a hash of the server's public host key. If you accept it, your client stores a copy of that public key in a file called known_hosts. Every future connection, your client checks that the server presents the same public key. If it changes, SSH will scream at you and refuse to connect. This is your first line of defense against man-in-the-middle attacks. Without this check, a hacker could pretend to be your server and capture your login credentials. Now let us get into the real meat, the key exchange. SSH uses a clever method called the Diffie-Hellman key exchange. Do not let the name scare you. The idea is actually beautiful. Your client and the server each generate a temporary secret number. They never send that secret over the network. Instead, they combine their secrets with some public numbers, do a bit of modular math, and end up with identical shared secret keys. Even if a hacker is listening to every single packet, they cannot compute that shared secret because they do not have the original private numbers. This shared secret is then used to derive a symmetric encryption key. From this point forward, all data between your client and the server is encrypted using a fast algorithm like AES. So even if someone captures the traffic, all they see is gibberish. But hold on. We have encryption now. The server knows who it is talking to? Not yet. We have only encrypted the channel. We have not verified that you are actually you. That is the authentication phase. And this is where SSH gives you options. The most common method is password authentication. Your client sends your password, but this time it is encrypted, so it is safe from eavesdroppers. But passwords have problems. They can be guessed, stolen, or phished. A much stronger method is public key authentication. Here is how it works. You generate a key pair on your local machine, a private key that you keep secret, and a public key that you copy to the server. When you try to log in, the server sends a challenge, a random piece of data encrypted with your public key. Only your private key can decrypt it. Your client decrypts the challenge and sends it back. The server verifies it is correct. If it matches, you are in. No password ever crossed the network. This is why key-based authentication is considered the gold standard for security. But what about the user? Do you just type SSH username at server.com and wait? Well, there is a lot happening under the hood. The server runs an SSH daemon, usually called SSHD. It listens on port 22. When a connection comes in, it forks a new process to handle that session. That process handles the key exchange, the authentication, and then spawns a shell or the requested program. All of this happens in under a second, but behind the scenes the two machines are doing heavy cryptographic lifting. And if you use SSH for more than just shell access, like tunneling or file transfers with SCP, the same encryption protects that traffic too. In fact, you can even forward local ports through an SSH tunnel, creating a secure VPN-like connection for other applications. Real-world use cases go way beyond logging into a terminal. System administrators rely on SSH to manage fleets of servers, deploy code, and run backups. Developers use SSH to push code to GitHub or GitLab. Security professionals use SSH to create encrypted tunnels for bypassing firewalls. In fact, many cloud providers, like AWS or DigitalOcean, require you to use SSH keys to access your virtual machines from day one. Without SSH, the modern internet would be a much less manageable and much more dangerous place. But SSH is not perfect. Let us talk about some pros and cons. On the plus side, it is incredibly secure when configured correctly. It is open source, so it has been audited by thousands of eyes. It supports multiple authentication methods, port forwarding, and even X11 forwarding to run graphical applications remotely. On the downside, the initial setup of key pairs can be confusing for beginners. If you lose your private key, you could lock yourself out of your server permanently. Also, the default port 22 is constantly hammered by bots. If you leave password authentication enabled, your server logs will fill up with thousands of failed login attempts from automated scanners. Another downside is that SSH does not have built-in session recording or user management for large teams, so you often need to layer tools like sudo logs or SSH certificates on top of it. And speaking of common mistakes, let me save you some headaches. The number one mistake is leaving root login enabled with password authentication. Do not do it. Disable permit root login in your SSHD config. Number 2 mistake is using weak encryption ciphers. Old SSH versions support outdated algorithms like RC4 that are easily broken. Make sure your server and client are up to date and configured to use strong ciphers like AES or ChaCha20. Number 3 mistake is forgetting to manage your known_hosts file. If you rebuild a server and get a new host key, your client will refuse to connect. You have to manually remove the old key from known_hosts. And the sneakiest mistake of all is copying your private key to a server. Never, ever do that. The private key stays on your local machine. You copy only the public key to the server. If your private key is on a server, and that server gets compromised, the attacker now has your identity. Let me give you a quick mental model for all this. Think of SSH as a secure tunnel through a dangerous city. The TCP handshake is like agreeing to meet at a specific street corner. The key exchange is like you and the server both shouting random numbers to each other, but using a magic trick so only you two can figure out the secret meeting place. The host key verification is like checking the server's ID badge. And the authentication is like you showing your own ID through a peephole, without ever passing the ID over the street. The entire time, you are walking through a transparent pipe that only you and the server can see into. That is the beauty of SSH. So the next time you type SSH and hit enter, spare a thought for all the cryptography happening in the background. From Diffie-Hellman to AES to RSA signatures, every layer is working together to make that connection safe. And if you ever wonder why your SSH feels slow, now you know it is because your computers are doing complex math to protect you. Thank you for sticking with me through this deep dive. If you found this helpful, please smash that like button and subscribe to Dev Brief. We make complex tech topics digestible, one video at a time. See you in the next one.